Hello guys, so welcome to my video. In this lesson, we are going to extend our discussion about the dot product. So what I want to do here is first we're going to prove the converse of the definitions, which is proving from geometric definition to algebraic definition. And also we are going to talk about the relevance of dot products, why we are using it when we are dealing maybe with geometric problems or even physics problems, and as well as linear algebra for vectors, which can help us to prove our two definitions being equivalent. So let's get started. Let's recall what is geometric definition of dot product. So if we consider there are two vectors a and b, and notice that when we are dealing with two vectors, that we need to take a note that these two vectors, when we operate translations, and they can form a plane. And because of that, we know that if we put their tails on the same point here and they have an angle which we call it theta, then the dot product is defined as the magnitude of A times magnitude of B times the cosine angle theta. Okay. So our proof strategy is similar to what we have discussed before. So we need to test the properties of given definition. So what are the properties that we need to consider? First thing is the commutative property, which is straightforward. You can just look by your eyes and then you can conclude it in milliseconds that this is holds, right? And second, the most important things to note is that when we are proving this, do not consider that, do not even accept that distributive property is hold when trying to prove this definition, since we only prove that distributive property is true when we are dealing with algebraic to geometric definition. Okay, so this is need to take care of. uh, okay, so this is the proof. So imagine that we have three vectors here, a, b, and c. Actually this is the arranged one. In diagrams you might have a, b, and c spread out in the space. So just take a random examples, and if you perform the translations, then it can be shown. I mean, it is directly obvious that we can form this, right? A and B connected by one tail on a one point, and then B, the head of B is the can be C is the continuation of head of B, so is its tail and the head of B means in the points. And also we can state it in mathematically of distributive property as follows, that a dot b plus c equals to a dot b plus a dot c. Notice that I draw a cylinder here because this will help us proving the laws, as we will see later. I mean, soon enough. So the first thing that you need to do is to set the A as your axis of the cylinder here, and then after you set it up as the axis, then consider the 3 points, these points, these points, and this point. Okay, and then for each point we draw a circle such that it is parallel to the base of the cylinder. Yeah, for this is the base, and this is also the base, and perpendicular to the axis, and contains one of these points. So we got three orange circles here. this for this point, and this point. And then what we need to consider next is just looking by geometry. If we have A as our circle, then what happens if we draw a line from here to here? This will be perpendicular, right? So by definition of dot product, then we got this length as our um, projection of B, right? Bx. I should say not Bx. B projection to A, right? If we consider a previous definition here, if we take B cosine of theta first, then what's the meaning? What is the meaning when we consider it geometrically? So we have vector B, and we have also another vector that is projected into A, but its length is defined by B cosine theta. Okay. In geometry, we're not dealing with vectors. We're actually dealing with just the lines. But if we're just dealing with line, then we can just add some magnitude of B, which means the length of the line, right? So this is B cosine of theta. I'm sorry. Uh, so what I mean here is, if we consider the left hand side of these equations, then what we are doing here is essentially taking the sum of B plus C, which is connecting these dots and this dot, right? This will form B plus C. And what we have, we know that this is also the center of circles, just the extension of the line of A. And then we also know that this and this is perpendicular, right? This line. We draw some kind of line such that it will perpendicular to the axis of A. So B plus C. If we project this into A, then we got this length, right? And similarly for B and C. For B, if we project it to A, then we get this length. And C, if we project it to A, then we also get this length, right? It's actually can be projected as this one, but you can just translate it and you will form this line, right? So we have a line that is projected by B, and we have a line projected by C, and we also have a line that is projected by B and C. Actually, I draw it in separate lines just to avoid the confusions. Okay, so this is projected by B, projected by C, projected by B plus C. And we know that from basic geometry, if we have length L1, L2, then what is the length of this one? It's just L1 plus L2, right? In other words, what this equation tells us the same thing as this our basic geometric knowledge, right? So A dot B tells us about uh, the projection of B to A, and A dot C tells us the projection of C to A. Okay. So we haven't completed our proof yet. It's just proving the distributive property of dot product of vectors. But before we continue, we need to understand some concept borrowed from linear algebra. So the most important concept is basis. So before we understand basis, we also need to consider the following. First one is the linear independence of vectors and linear combination of vectors. Don't get scared by this terminology, as we will see, as we will discuss further, dive further into these two things like after this slide. And also, after we discuss the basis, we will also discuss the orthogonality, which is tells you the importance why we need to use dot products. Okay. So before we move on to the formal definition, actually it's not that formal, but anyway, we just need to have some convention first. So when I say a set of vector, I represent it as a v, okay, equals to curly brackets of vectors, right? v1 is vector, and vn is vectors, and we have v1, v2, x, blah 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 till vn, and where the number of rows for each vectors is m. So actually we need to represent our vector instead of like xyz or ijk, we need to represent it in a matrix form. So how to represent a vector in 3D in matrix form? So if we have the our usual representation of vectors in its component, so if we have x hat plus y hat plus z hat, then we can represent it in this form of matrix. Okay, I think this definition is quite straightforward. So notice that n and m is not necessarily the same. Okay, because I just want to give some more complexity regarding, or maybe technicalities about what happens if n and m is not equal. So let's go to linear independence. So we a set of vector v where the number of rows for its vector is m. So these vectors are actually linear independent of each other if and only if. So I hope you understand what does it mean when we call something if and only if. So if and only if means linear independence implies this, and this all of things implies linear independence. Okay, I think that's quite straightforward. Um, if we have a constant vector c, which is defined as follows: c1 up until cn, which is equals to 0, where a 0 factor is actually represented as each element are 0 in the vector, and of course the number of row is n here. So so c is the only solution for the following equation: sigma from I equals to 1 to n ci vi equals to 0. Okay, well, if you don't if you're not comfortable with sigma notation, well, you can just try to expand it. So c1 v1 blah blah to cn vn equals to 0. Okay, so maybe it's not making any sense when you first try to look at this, but let's make some consider some special case. Okay, so let's just consider that when n equals to 2, okay, and m equals to 2, suppose we have vector v1 and we have vector v2. Okay, um, in this diagram, can you convince yourself that if we have constant c1 and c2 such that c1 plus c1 times v1 plus c2 v2 equals to 0? Yeah. This yeah, there exists a constant if and only if c1 and c2 equals to 0, and this is the only solution. Why? Because when we want to, let's say, to make v1 becomes equals to 0, then we need to play with v2, right? We can only play with scalar multiplication of v2, but we know that scalar multiplication only change the value of v2 in this direction only, right? So if we want to modify the vector v1 by the scalar multiplication of v2, um, if we either subtract it or add it, it's impossible to make it 0, right? Because 0 can be written as v1 minus something, right? X. But here this means that x should equals to v1. But x will not equals to v1 because x is equals to constant multiply times v2. But constant multiply times v2 is only lies on this line, so it's impossible to make v1 become 0, right? I hope this makes sense. So there's something that we need to consider, because I said before that n not necessarily equals to m, but I want to think in larger dimension. Okay, so consider the scenario where n is bigger than m. So what happens? Well, by looking at this, there are n set of, there are n vectors in a set V, and the number of column is m. So use this following idea actually, where we have learned this before in maybe first year of your high school maybe. To solve linear system with n unknowns with unique solutions, okay, I make it capital so it's only applicable for unique solutions. We need at least n equations. Okay. Um, so to make this more clear, let's say if you have equations a1 x1 plus blah 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 till a um, n x n equals to let's say we're just solving for equals to 0 for everything. Okay, just I just want to relate this to our linear independence concept and so on until we got maybe I will make it double index for a. So a 1 1 a 1 n a m 1 x 1 blah 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 plus a m n x n equals to 0. So why the hell I wrote this equation? Because if you expand our our definition, as you can see here, the c, when we replace c with x maybe, okay, sorry for symbol confusions, just represent c with a actually. I'm sorry. I just want to represent linear system equation, but actually the definition of linear independence can be written as follows: c1 v1 1, okay, blah 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 v, because there are n rows, m rows, so v1 m. Okay, so maybe I just change the index m1. Okay, this all refers to vector v1 plus c2, the same things, 1 2 blah 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 2 vm2, and so on until cn v 1 n blah 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 2 v mn equals to 0. And somehow we can represent this as this form. So just replace everything with v here. So how many equations that we have here? How many equations? There are m equations, right? And how many unknowns? There are n unknowns. So what this tells you? This tells you that if we want to get the unique solution, and the linear independence also requires us to get c equals to 0 as the only solution, right? So of course, if we plug x, all of x are 0, then those x are the solutions. But there are another things that we need to consider, is that whether this solution is unique or not. So that's why we want to prove the part of uniqueness. So because here we have n bigger than m, we have more unknowns than the equations, then this tells us that the solution is not unique. Okay, so therefore, if n bigger than m, then it is impossible to get the linear independence condition. Okay, now let's consider what if n equals smaller or equal to m. Then again, this does, but you need to take this warning that this doesn't mean that your solution guaranteed to be unique. Why? Because there might be some set of linear equations where it's redundant, right? I mean, um, we can increase number of equations by adding more rows, right? And it might be the case that another equation just a scalar multiplication of some constant. So that's what we call redundant. Okay. Now after we discuss about linear independence, we need to consider a linear combination. So linear combination of vector v can also form another vector, which we will call b, by choosing any value for constant vector c. So basically, not any vectors. If we choose a specific value for ci, let's and we multiply it by each vectors in the set, and we take the sum, then this resulting sum would be vectors, right? So we call that v. But now the interesting thing that we want to consider is the span v here, which is defined as the collection of all possible linear combination of vectors in v. Okay, so this means that we can generate many vectors as we want by picking various value of c. Okay, so maybe let's say c1 is starting from 0, then maybe we will iterate c2 from 0, 1, 2, 3, and so on till infinity, and also for negative value until minus infinity, and for c3 and so on. So, sorry, this is not a formal definition, by the way, because we can also pick value of c as either real or complex value. Okay, so we try every combinations of c such that value of c is lies on either real or complex value depending on the specification. Well, when we discuss about classical mechanics, or maybe classical mechanics, I think we rarely deal with something complex coefficients here. Okay, so that's the idea. Now we can talk about basis, because there are two requirements for a set of vector v to form a basis for some vector space Rn. So you don't need to confuse much about what is vector space. Basically, 2-dimension, we can just write it as R2, 3-dimension as R3, and so on. So the first condition is that they must be linearly independent. So why we need to define a basis in this way? Because we have previously talked about the value of n and m. When we set n small or equals to m, there might be some redundancy that makes the solutions for a linear equation becomes non-unique. Okay, so they must be linearly independent, so as to remove redundancy of the vectors. Okay, that's the idea. And the second one is that they must span Rn. So our mainly purpose why we need to form a set of vectors is that we want that such that it will span Rn. Okay, if we're talking about a vector with we need to span Rn, because, well, if we consider R3 or R2, I think it's quite pointless to make, if we want to try to make a linear combination of, for instance, in R2, it's sufficient to make it like two vectors like this, as we have discussed here. And R3, basically we just need to represent as 3 vectors such that it will span all of the vectors possible in R3. Okay, so basically R3s are all possible vectors. Okay, for vectors that has 3 columns, whereas R2 is it's 3 rows. For R2 it is 2 rows. Okay, so that's the main point of basis. So let's just go to the example. If you think that I know that the first time encounter this concept might be confused, but let's just take a simple example that we will use in the future proof. So example where consider that V is just a set of vector of x hat, y hat, and z hat form basis of R cube. So I want to prove that this is the case, but just write the notation in matrix form. So x just 1 0 0, y equals to 0 1 0, and z equals to 0 0 1. So what we need to prove is first they should satisfy linear independence. Should be, if we want to solve this equation, c1x plus c2y plus c3z equals to 0, what happens? So basically just write it like this. So there's no 0. We got as this, right? If well, this is trivial, right? Because here we got c1 equals to c2 equals to c3 equals to 0. There's no another solution. Therefore, this vectors set of vector is linear independent. And the second thing that we need to consider is the linear combinations. So let's say for any vector v in R cube, we want to find a constant c1 x plus c2y plus c3z such that this is equals to v. Okay, so let's represent v as v1, v2, v3. Okay. So here obviously we got c1 equals v1. Okay, c2 we can set c2 to be equals to v2, and so on for c3 equals to v3. So it means that for any vectors that can be represented vectors in R3, which we can represent it as these 3 rows vectors v1, v2, v3. Then by straightforwardly plugging in the matrix here, we got c1 equals to v1, c2 equals to v2, and c3 equals to v3. So it means that as long as we know v1, v2, and v3, which is the case for any vectors in R cube, then we can determine the values of c's. So therefore, this set of vectors is span R cube. Is span equals to R cube. Okay. So after we have discussed about basis of vectors, but now we should focus our attention on 3D vectors, which is R cube. And by looking at the definition of geometric dot product, we notice that x dot y equals to 0. Why? Because x is here, y is there, and they are perpendicular. And as long as they are perpendicular, cosine of 90 degrees is just equals to 0. Okay, so that's why x dot y is equals to 0, and you can extend it for x dot z equals to 0, y dot z equals to 0, right? Now x dot x equals to 1. Well, it's obvious because cosine of 0 is just 1, and the magnitude of unit vectors is always 1. So the dot product is just 1 times 1 times 1, right? Which is equals to 1. And you can similarly do for y and z. So from the previous slide, for any vector v that is part R cube, we have discussed before, there will be exist a constant xyz such that xx plus yy plus zz equals to v, right? Because v lies on R cube and x hat, y hat, and z hat spans R cube. So that means, and they are linearly independent, we can uniquely represent v as this linear combination of vectors. Okay. So what happens if we take a dot product with respect to x on the both sides? We get this, and then by looking at the properties that we have discussed before here, then we know this equals to 1, this equals to 0, this is equal to 0, and we end up with x equals to v dot x, and we know that if we do the calculation similarly y and z, it actually turns out as this form: x plus v dot y, y plus v dot z, z equals to v, right? And we know that in projection method we can write it as vyy plus vzz equals to v, right? So therefore, this is actually a projection of vectors into x, y, and z. Okay. Notice that if a set of vector form basis and we want to represent any vectors that lies on R cube, which is v here, then we can uniquely determine the constant of x, y, and z for a linear combination of a set of vectors that is form a basis for R cube here. Okay, so it might take time to understand this concept actually. So to complete our proof, uh, we need to consider the following dot product actually. So a dot b, what is a dot b? What happens if we expand b in terms of its component in x, y, and z as our vector space? So we basically get a dot, maybe not using sigma because we're just dealing with three things. So bxx time plus, sorry, byy plus bzz, and then we have proved the distributive property of dot product for geometry. So we got, sorry, bx a dot x plus by a dot y plus bz a dot z. And from the previous slide, we defined that the components of Vx as the dot product of V with respect to the unit vector of x. So here we can write it as Ax, right? Here as Ay, here's as Az, right? And by the commutative property of multiplication, we just write it as Ax Bx plus Ay By plus Az Bz, which is the algebraic definition of dot product. So we complete our proof here. So now let's briefly talk about the relevance of dot product. First, dot product of two vectors is 0 if and only if they are perpendicular, and second one is the projection method. So when we're talking about projection, it means that we are doing the dot products, okay, actually. And third one, dot product is essentially cosine's law. So if you saw my previous video for dot product for algebraic definition, proving algebraic definition to geometric definition, we see that we involve cosine's law, right? And you got the dot product of two vectors is actually somehow related to cosine's law. Okay. And the dot product is also useful for our analytical tool for geometric problem because we can convert the definition of dot product from geometric perspective into algebraic perspective. So That's it for today. I hope this content of the lesson are useful, and we will see you later in the next video.